Good evening, everybody. So, we are talking about the naming of the coordination compounds. So, how we systematically name one compound to the another, and in this case we basically consider the entire complex within the square bracket. Then we have the metal and the different types of ligands, say L1, L2, L3, etc. And while doing so, we will find that this particular metal center, say if it is iron, we have iron there, and depending upon the nature of the different oxidation states, it can present there as +2 or +3 or +4. So, whenever we name the entire compound, we will also detail the nature of the metal ion, what metal center is present within the complex species and its different oxidation states, as well as the nature of the ligand, starting from the simple salt what we know. After dissolving any metal salt in water, we get the corresponding aqueous compound. So, when we put the aqueous compound with that of the metal ion in one particular oxidation state, we will also explicitly define and state in the complete naming of the compound that whether this particular ligand is present as a neutral species or an ionic one, or sometime as the cationic one. When some of these compounds, say some iron salt is reacting with NO as gas, nitric oxide gas, but it immediately giving up one particular electron and converted this particular species to the cationic species. So, knowing the nature of this particular ligand and its corresponding charge is also important, because that will balance the corresponding positive charge what is available on the metal center, as well as the other ligands, say L3 and L2, which can be neutral or which can also be anionic. And after that we can have some thing as the anionic charge balancing species, depending upon the overall charge of the complex species. If the overall charge on the complex species is cationic, if it is monocationic, we will have 1A of mononegative species, that means say perchlorate or nitrate or chloride. If it is a dicationic complex species, we will have A2 or some dicationic species like sulfate. Similarly, if this particular complex species, this can also be present as an anionic fragment also, and in that case, to balance the charge, we will have some cationic species like A. So, depending upon the charge on the anionic complex part, we will have the corresponding cationic species. It can be very well the same potassium ion or sodium ion or ammonium ion, and the corresponding charge, that means how many potassium or how many sodium or how many ammonium ion would be required to counterbalance the corresponding charge on the anionic complex. So, will the second part of this nomenclature part of the complexes, we will see that one particular example we have taken here where the iron center is present, and what we are just discussing, that we have the NO as some species present, and it is a well known compound. From our school days, we all use this particular compound as a very good analytical reagent. So, metal complex of iron can serve the purpose of an analytical reagent which can detect very nicely the presence of some other species. That means, this complex can have some characteristic signature which can be changed if it reacts with some other analyte. So, metal complex can react with some other analyte to give some change of the property of the metal complex. That means, some of the part of the metal complex, it can be the metal ion, it can be the other part, that means the ligand. The first ligand is Cn minus, the cyanide ion, or the nitrosyl cation. This NO is present over here as NO plus, as nitrosyl cation. So, the entire compound can react with sulfide ion S2 minus for its detection, and this NO plus is basically reacting with S2 minus, giving rise to the corresponding another anionic species which is NOS. So, how we can name this particular complex, because it has all these things are there, the metal is present, this can be considered as L1 and NO can be considered as L2, and this particular part, the entire part is the anionic part. So, we need the presence of K, that means the potassium, or the cationic part, and this particular cationic part can be counterbalance the corresponding anionic charge on the complex and the number of water molecules as water of crystallizations. So, this particular compound, nicely when we name the compound, we should have some good idea about what type of compound is it. So, we have 4 cyanide ligands. So, all of them are same, and one is NO. So, NO is binding towards the iron center through its nitrogen atom. So, directly you can have this iron nitrogen bond coming from the NO, and we have the 2 Na plus, because the complex species has 2 minus negative charge. So, how we can name this particular compound, and the nature of the compound is also well known, is a very good red crystalline, dark red crystalline compound, is in powder in nature also. And since it is a sodium salt, because we can have all other different salts also possible, we can go for the corresponding potassium salt, we can go for the ammonium salt as well, but this particular compound is very easily made in the laboratory, and the red beautiful compound is basically give us the corresponding good solubility in water, because this complex is a sodium salt, and as we all know, the sodium salts are highly soluble in water. So, it has good solubility in water, and in water it gives some red colored solution. So, when this compound reacts with sulfide anion, say S2 minus, and this S2 minus can come from sodium sulfide and this basically react with the NO plus present in sodium nitroprusside. So, this which is present, this fragment is nitroprusside NPS, or we can fully name as, when it is sodium salt. So, it is SNP, sodium nitroprusside. So, when they are reacting, it basically gives us NOS minus. So, which is very much similar to some other pseudo halides like azide, which is also having 3 atoms. So, 3 atom anionic species, or thiocyanate anion, or NCO minus anion. So, the characteristic reaction towards the complex formation is well known to us. As we all know, a solution of iron in the ferric state, that the solution of ferric chloride in water immediately reacts with the thiocyanate anion to give red blood coloration. So, it basically gives red blood coloration. That means, we can detect the presence of thiocyanate anion by knowing the color change from a very light yellow solution of ferric ion by the corresponding SCN minus anion as potassium thiocyanate or ammonium thiocyanate, which is also colorless, but when it goes to bind to the iron center, it gives a very characteristic red blood color, which can be identified as the formation of the complex species based on FeNCS bond. Similarly, here also the in situ generation of NOS minus of sodium nitroprusside, which is still bound to the iron center, gives a corresponding color change. We get a violet coloration from a change of the red color of sodium nitroprusside. So, what we see that how we can name this particular compound, we can also see how this particular compound can be very easily made from a well known another complex, which is potassium ferrocyanide. When K4FeCN whole 6, the iron is present in the +2 oxidation state. So, we have 4 potassium ions are required for charge balance, and this is known as potassium ferrocyanide. The iron oxidation state is important. It is in +2 oxidation state, and it can be oxidized to its corresponding ferric form, which is K3FeCN whole 6, which is known as potassium ferricyanide. So, for the synthesis of sodium nitroprusside from potassium ferrocyanide, we react it with nitric acid. So, reaction of this particular species with nitric acid gives rise to the generation of this complex anionic species, that means FeCN whole 5 NO. That means this NO, that means nitric oxide gas, is in situ generated from nitric acid. The way we know that the different forms of nitric acid, the cold, the hot, the dilute and the concentrated nitric acids can react with copper metal to give different nitrogen oxides. So, this is a standard technique where we can make different nitrogen oxides by reacting nitric acid with the copper, the metallic copper. Similarly, in this particular case also is nitrogen is present in +5 oxidation state, which is getting reduced during this particular transformation, and NO is forming, NO is generated in situ from the medium. So, that generated NO is immediately going to react with the FeCN with the expulsion of 1 CN. So, 1 CN minus is removed from there, and that particular position, that means 1 CN is going when we have all 6 CN groups are attached in the ferrocyanide. So, 1 is substituted by NO. So, we get this particular anionic species, but in protonated form, that means H2 salt, the corresponding H2 salt is also possible with the liberation of carbon dioxide and separation of ammonium nitrate and potassium nitrate. Then in the next step, this acid form of sodium nitroprusside, that means the protonated nitroprusside, the protonated nitroprusside is reacted with sodium carbonate. Since it is also acidic in nature, it immediately reacts with sodium carbonate with liberation of carbon dioxide and water, and the compound is getting transformed to its corresponding sodium salt. So, that is why this is the procedure where we can prepare sodium nitroprusside from potassium ferrocyanide. So, this particular thing directly gives us that one particular potassium salt of the complex to its corresponding sodium salt. So, there is one more technique also available for the production of this ferrocyanide. This is very interesting and nice molecule which has importance for analytical chemistry as well as the structure and the corresponding iron complexes. So, like nitric acid, where we are providing nitrates as anions, here nitrites are also we are providing, and we all know this analytical test for nitrate and nitrites using the ferrous sulphate solution. The cold ferrous sulphate solution is the laboratory is through the brown ring test, and that brown ring test also gives us the corresponding NO plus attached to the iron center with 5 water molecules there. Similarly, these two reactions, these two synthetic procedures, that means the production of sodium nitroprusside, gives us these important informations that both nitrate as well as nitrite ions can generate NO species with the reaction of sodium or potassium ferrocyanide. So, here NO2 minus is providing us with the corresponding NO with the liberation of 1 Cn minus anion and 2 hydroxide ions. So, this differentiation for this type of ligands and the number of ligands, because in this particular case what we see that we have two types of ligands, one is the corresponding Cn minus and another is the corresponding NO. So, when large number of these ligands are present and during naming the corresponding compound, we basically indicate the corresponding numbers as the corresponding prefixes as di, tri, etc. That means, when we have 2 ligands we call it as a di, when we have 3 such ligands we call it tri, and when we have 6 or 5 cyanides we call it as a pentacyano or hexacyano species. But the rule is not applicable to all. When we have organic polydentate ligands, that means say some polyamines or amino acids are there, when the ligands present, that means simple ethylene diamine, En is ethylene diamine and EDTA is ethylene diamine tetraacetic acid. When they are going for deprotonation, it gives ethylene diamine tetraacetate anions, have 4 anionic charges. So, this ligand has already ethylene diamine. So, diamine part is there and which is ethylene diamine tetra, di and tetra, both the two terms are there. So, in that particular case we will consider instead of di or tri in the normal case of nomenclature, like the presence of 4 chlorides or 4 nitrates or 2 chlorides or 3 nitrates, we call them as bis, tris or tetrakis. So, wherever we have the normal ligand nomenclature as mono, di, tri, tetra, penta and hexa will be considered as bis, tris, tetrakis, pentakis and hexakis when we have polydentate organic ligands bound to the metal center. So, how we name this particular example of the complex where chromium is attached to 2 chloride anions and 4 water molecules, and the ligands present are therefore 2 types like that sodium nitroprusside. Cl minus is one ligand which is anionic and water as the another ligand which is neutral and forming the direct bond with the metal center through its oxygen atom. So, when we have the monodentate ligands like Cl or H2O, we name them as chloro or aco, and alphabetically we will find that A is coming before C, therefore, aco names will come before the chloro. And there are 4 such aco molecules and 2 chloro ligands. So, we will also add the numbers as prefixes, and since these are not polydentate organic ligands, we will simply use the first type of nomenclature for the reaction where we define the number of aco molecules and number of chloro ligands. Therefore, the naming would be like this. The coordination compound would be called as therefore the tetra aco dichlorochromium 3. So, we have 4 water molecules surrounding the chromium and 2 chloride anions. These are also they are direct ligands, and chromium is in +3 oxidation state. How we know that? Because we have 2 charges, 2 negative charges are balanced by Cl groups. So, this here should definitely be in the trivalent state, that means in the chromic state. So, chromic ion is bound to 2 Cl and 4 water molecules. So, we get a typical octahedral molecule. Since the complex is in here, one square bracket would be there. So, since the complex is in a cationic form, that means the cationic species we have. So, outside the coordination sphere we can have other mononegative anionic species like nitrate, perchlorate or Cl. So, if the entire compound, if it is the corresponding nitrate salt of the metal complex of Cl and water ligands of chromium, we get the corresponding full name of the corresponding compound as tetra aqua dichlorochromium 3 nitrate, if it is a nitrate salt. Similarly, we go for the corresponding polydentate ligand, which is COCl2En whole twice. So, in this particular case, what we will see that we are bringing the polydentate ligand in our hand, that means the ethylene diamine, which is NH2 and NH2, and since the compound is cobalt COCl2 En whole 2. So, we have this ligand, 2 such these ligands. So, 2 of these bidentate ligands are there. So, if we have again 6 positions, and depending upon the cobalt oxidation state, if it is 3 plus, we can go for the corresponding charge balance by 2 Cl minus. So, overall charge of this complex would be again plus, and 2 of these positions are occupied by Cl, which in most cases can come from the starting metal salt what we are using for the synthesis of the compound, that means cobaltous chloride, that means cobalt 2 chloride with some amount of oxidation by passing air or hydrogen peroxide. So, 2 of these chlorides are still present with the cobalt, and 2 more are occupied by these 2 bidentate ligands of ethylene diamine. So, we get a typical octahedral compound where the cobalt is bound to 6 atoms, 4 of them are coming from the nitrogens of ethylene diamine. So, it is CON4 and 2 of them are Cl2. So, CON4 Cl2. Since the charge is like this, so it can also be a corresponding nitrate salt, which will be outside the coordination sphere, and we have overall charge of this particular big cationic complex species is +1 and this is -1. So, we have a complex species which is 1:1 type of electrolyte, and we can measure the corresponding solution electrical conductivity or solution electrical conductance to identify the corresponding nature of this particular compound. So, we have 2 types of these ligands, and metal we all know CO is cobalt. So, we should be having a name where it can be prefixed with ethylene diamine, because already the name contains the di. So, we cannot use di as the prefix of ethylene diamine. So, di will be converted to bis, as we have seen just now in the list, that bis will be used in before the corresponding number of ethylene diamines in the bracket. So, the compound would be dichlorobis, C is coming before E again in the alphabetical order. So, dichlorobis ethylene diamine cobalt 3 ion is formed. So, if the complex species is written in the form of positive charge, we can call it as a cobalt 3 ion, but if it is the corresponding salt, that means the nitrate salt or perchlorate salt, we will name it as dichloro-bis ethylene diamine cobalt 3 perchlorate or dichloro-bis ethylene diamine cobalt 3 nitrate. Similarly, we just concentrate our attention while we name the corresponding metal center and its oxidation state. Just now we have seen how we can assign the corresponding metal center if we do not know the corresponding exact oxidation state of the metal center. If the metal center has undergone some oxidation like cobalt 2 to cobalt 3 by the oxygen present in the air or by using some reagent like hydrogen peroxide. So, assignment of the metal oxidation state is therefore important. So, formal name of the metal and the oxidation state we should know, and we should number the corresponding oxidation state in Roman numeral within parenthesis. So, for +3 the chromium and cobalt should be written as Roman 3 within bracket, but in case of copper the oxidation state of +2 is denoted as copper 2. So, if we have the different oxidation states, so we should not have any confusion regarding the identification of the oxidation state. We should straightway name the corresponding oxidation state as +2 or +3, or sometime we can have any metal oxidation state as +4. But if we see doing such operation on naming of these compounds, the overall charge on the complex is anion. So, we can have some metals are there and we can have the corresponding name. When it is copper, we name this as copper 2. If it is the corresponding tetraamine copper salt, so we call it as a tetraamine copper 2 ion. But when we have the corresponding copper 2 present, but more number of anions are surrounding the copper center, giving a corresponding anionic charge on the complex species, we will name this particular copper center as cuprate 2. So, how we get that? We just get, if we have copper 2 chloride in our hand and if we see some amount of chloride ligands are still attaching to it, and if all the 2 chlorides, the new ligands are attaching to the same copper center, the corresponding formula of the complex species would be CuCl4, because copper has a typical tendency to bind 4 ligands around it in a particular geometry. It can be square planar, it can be tetrahedral, or it can be something related to some distortions related to these 2 geometries. So, when we have 4Cl minus, that means more and more charge is accumulated on the dipositive copper center. So, overall charge on this complex species would be 2 minus. So, in this particular case the naming would be completely different and copper 2 will be named as now cuprate with the identification of the oxidation state. Similarly, we can have the corresponding cations also. The cations should be named first. So, ammonium ion, if it is present, completely balancing the corresponding negative charge on the complex species, we should name the ammonium ion also along with the corresponding 8 nomenclature on the anionic form. So, copper 2 will become cuprate 2. Similarly, there are some more Latin names we can use compared to the common English name of other metal ions. If we iron is get, that we all know that iron, the symbol is Fe, that means it is coming from ferrum. So, when we use the Latin name for the corresponding anionic species, we call it as a ferrate anion. Similarly, the copper we have just now seen will be cuprate, tin will be related to the stannate. silver would be named as argentate, is related to the corresponding name, basically Latin name of the element. Lead will be plumbate, gold would be aurate. So, the oxidation state will define and the anionic form will also define, but if we have the other metal ions not belongs to this Latin name, the other metal ions will simply have the 8 nomenclature. Cobalt, addition of 8 will be cobaltate, nickel will be nickeltate. When we add 8, when the species will be in the anionic form, zinc would be zincate, osmium would be osmate, cadmium would be cadmate, platinum would be platinate, mercury would be mercurate, etc. And the suffix end tends to replace the um and ium if present, and ium. So, osmium was there, so mium was, so mium. So, that ium has gone from osmium and this has become osmate. Similarly, cadmium, the ium is gone, so cadmium become cadmate, and zinc is there, zinc full name is there with that of the addition of 8, and if in other cases the is also there along with ium, that also will go, that will be replaced by simply 8. So, that nomenclature will give us some good idea about how we name the very simple species like that of the addition of say CrCl4, if it is in the +3 oxidation state, it would be CrCl1 minus. And why we are talking all these things? Because it is very important, because most of the metal salts we know can be available as its corresponding chloride salt very easily by the use of hydrochloric acid with the reaction of corresponding hydroxides or carbonates. So, these chlorides, when they are taking up more number of chlorides, can be the corresponding example, very simple example for the anionic complex. Similarly, when this chromium or iron or anything is bound to water molecule, the neutral water molecule, and we all know, we have been discussing this for several our classes, that when iron in +3 oxidation state is bound to one water molecule, we have so many of this type of FeO bonds, and the pK of this bonding will change compared to the free water molecule, and we get immediate deprotonation. So, deprotonation will take place, and this deprotonation will give rise to FeOH species from FeOH2. Similarly, if we can see that we have more number of these groups, that means if we just consider 4 such water molecules were there, and we can have 4 different pK values, pK1, pK2, pK3 and pK4, and after all deprotonation it gives rise to some FeOH type of species which will have a negative charge, because this type of species are very useful also, because when they are forming as the mononuclear fragment, it immediately can go for the bridging, because compared to iron, this hydroxide anion has some more potential, which is more effective to bind two metal centers, and these are plenty in nature. In natural minerals and ores, we find that corresponding oxo-hydroxide-bridged iron centers are present. Also in the biological systems, the iron bound by oxo or hydroxo functions are plenty in number. So, if we just see that the same thing is happening over a chromium center. So, when we have chromium bound to 4 hydroxide groups and the complex is thus becoming anion, because this chromium is present in +3 oxidation state. So, we have monodentate ligand. So, we do not have any polydentate organic species present. So, the tetra nomenclature is fine instead of tetrakis, and hydroxo groups are there. So, tetrahydroxo species is forming over there, and this tetrahydroxo species is also possible for any metal center. Therefore, it can be with iron, it can be with cobalt, but it should be known to us that only 4 ligands are present around these 2 chromium center. Otherwise, we will be missing 2 other positions if it is a octahedral one, and if we write this one only, we should consider that 2 other positions, the remaining 2 positions should be occupied by simple water molecules. So, the chromium we have, so already we know the rule that 8 nomenclature will be attached to chromium with the elimination of IUM. So, IUM will not be there and the name would be chromate because the oxidation state is +3. So, we replace the name as 3. So, we have the naming of this compound CrOH whole 4 minus would be tetrahydroxo chromate 3 ion. If it is a corresponding potassium salt, we will call it potassium tetrahydroxo chromate 3. We will have a full stop over here only. If it is a corresponding ammonium salt, we name it as ammonium tetrahydroxo chromate 3. So, the name of the cationic part, though it is not a complex part, it is a simple inorganic part. So, the simple inorganic part should also be named along with the complex part. So, we will see next the most important species what we are discussing, that arrangement of 4 chloride ligands around the copper center. So, when we attach 4 such chloride groups like chromium we have seen also, and in this particular case it is very easy to assume that it has only coordination number of 4. So, coordination number that we will discuss in our next class, that if we have within the complex species only 4 bonds are forming between metal and ligand. So, if we have only 4 ml bonds between metal M and ligand L, we will consider this as a species where the metal center has a coordination number of 4, and this is the limitation for some metal center, because some metal center can go low coordination number like silver, gold, etc. They can have a coordination number of 2, but in this case its number is restricted to 4. It is not going to 5 and it is not going to 6 also. So, the naming is very easy, as we have learned now. It would be tetrachlorocuprate 2 ion. If it is ammonium salt, it would be ammonium tetrachlorocuprate 2. So, this ion part will not be there, full stop will be here. So, some of these well known thing which is known in the literature and is known in the books also, that how we can consider some of these chloride complexes of copper chloride, that we are discussing, that this is the simplest cupric chloride compound. CuCl2 is the simple cupric chloride, and if it is reacting with more chloride, initially it can react with concentrated hydrochloric acid or any other chloride salt to give you CuCl4 minus, it would be 2 minus, CuCl4 2 minus, and if it is the corresponding ammonium salt, so ammonium salt is NH4 whole 2 CuCl4, the naming would be ammonium tetrachlorocuprate 2 And if we want to know the corresponding structure in the solid state, we grow the single crystals, and X-ray diffraction gives rise to the corresponding molecular structure determined by X-ray diffraction. We get something where we find that this is basically is not a tetrahedral one, it would be square planar one. And in crystal state, that means in the solid state, the crystal packing would be such that this particular one, this chloride center will share another chloride of the next molecule. Similarly, from the bottom side, from the lower side, it will also share another chloride of the next molecule. So, sharing of these free end of the chloride groups makes one particular center as a octahedral one, and which is not a true octahedral one having 6 coordination sites or coordination number of 6, but it would be considered as a 4 plus 2 octahedral coordination. 4 is from the same metal ion and 2 is coming out through sharing from the adjacent metal centers. So, the ammonium salt would be crystallizing as the corresponding species which would be octahedral in the solid state through sharing. But if we just try to crystallize it in its corresponding cesium salt, this would also be 2 minus like this, it would be 2 minus only. So, cesium 2CuCl4, which is cesium tetrachlorocuprate, but this time the structure is different because of this presence of this cation, because the size of the ammonium ion is small. So, we can get the corresponding networking or some supramolecular interaction between the CuCl4 2 minus species for chloride sharing, because whenever we have the corresponding crystal packing, we see that this is the anionic part. So, cationic part will be coming in between two anionic parts. So, there are some void spaces, and void spaces would be occupied by the cations. But in this particular case, the size of the cation is very less, which is ammonium ion. So, void spaces are of different type and which is very small and which is not inhibiting the corresponding sharing from the adjacent molecule through its Cl. So, if we have the cesium which is a bigger cation, individual species will remain as in a flattened tetrahedral structure, and we do not get such sharing of octahedral species. Similarly, if we have one type of bridging of this can be obtained in some potassium salt or ammonium salt of this KCuCl3 or ammonium CuCl3 with a mixed of these two, we get the potassium ammonium salt of Cu2Cl6, and these stack together to give the elongated tetrahedral coordination, elongated tetrahedral geometry around this particular copper, and we have the corresponding sharing of this. So, we get a chloride bridge dimeric form. Similarly, if the bridging is extended further, so it is another form of CsCuCl3 which is completely different from CS2CuCl4. So, this particular chloride, this is in the chain form. So, the chain is continuing in a zigzag fashion, and one chain also coordinates to the copper atoms to the other, giving this also a 4 plus 2 octahedral coordination in the solid state. So, in the solid state, one chain of one particular plane is sharing the other chlorides from the other chain, giving a typical octahedral. So, copper center, the copper metal center will always have some tendency to attract the other ligand which is already bound to the adjacent center of the copper. So, here also while we have the corresponding cations present, the name of the cation is coming first, then the anion. Now is another typical example of the complex where both the cationic part and the anionic part are the complex fragment. That means, we are not taking the help of any ammonium salt or any chloride or nitrate salt. We have made both the two parts, the cationic part as well as the anionic part, as the complex species. So, NH3 is the neutral. So, the first part is cationic and chloride is anionic. So, the second part is anionic. So, this is cation, this is anion, and it is going for the corresponding charge balance. So, we will write first the corresponding ammonium complex, the ammonia complex, followed by the corresponding chloride complex, because the chloride complex is correspondingly anionic, and the name would be therefore tetraamine platinum 2, the cationic part, and the anionic part is tetrachloroplatinate 2. So, is the anionic part and the platinate 2 nomenclature is operating over there. So, we get a complex species where both cation and anions are of complex nature. So, we can try with naming some more as the problem, where we have the octahedral cobalt center, where 3 chlorides and 3 ammonia molecules are attached. Similarly, we have the cobalt. In our future classes we will discuss the isomerism, where the isomerism will tell something related to the binding of the nitrite anion differently to the cobalt center, which is through oxygen. Here we have the cobalt oxygen bond, which are 3 in number, because we do not have any mixture between these. That means one is bound to nitrogen, another is bound to oxygen, but all are of same type. That means the nitrite is binding towards cobalt by oxygen atom. Similarly, 2 oxalate like ethylene diamine is bound to iron center, and we have 2 water molecules, and this is also not a complex species of mercury, but it is a complex species of the salt of silver. So, is the mercury belongs to the corresponding complex part, which is tetraiodo mercury anion, and is corresponding cationic part is the corresponding silver one. So, if we have more than 2, that means we have now the number of ligands are more, that means L1, L2 and L3, and depending upon the corresponding charge, the amine will be named first, which is the neutral one. So, the naming of the compound would be tetraamine, then alphabetically chloro will come next, then nitrito, which is bound to cobalt through nitrogen. So, it is tetraamine chloro nitrito N cobalt. So, N cobalt means it is immediately showing us that it is bound to the center through nitrogen. So, it is one isomeric form which is not bound to oxygen, but it is bound through nitrogen. So, it is bound to cobalt 3. So, it is the cationic form. So, it is the cobalt 3 ion, the name would be cobalt 3 ion. The in this particular case, the other isomer which is binding to oxygen. So, we instead of nitrito N we have nitrito oxygen also. So, the naming would be in that particular case, when NO2 is changed to ONO, we will get tetraamine chloro nitrito O cobalt 3 ion. Again it would be cobalt 3 ion, but instead of saying nitrito and nitrito distinction, we simply write nitrito N and nitrito O, mentioning that cobalt is bound through oxygen and bound through nitrogen. So, instead of nitro for NO2 and nitrito, these are some older definition that we write. When it is bound to nitro we call it nitro, and when it is bound through oxygen we have the nitrito. So, either we can write in the nitro and nitrito form, or the modern nomenclature we just write as nitrito N and nitrito O bind towards the cobalt center. Now, once we write this particular species as the corresponding compound, the name is in our hand. Now, the reverse one, that when we have the name, one particular compound name is given and you have been asked to write the formula. So, what type of formula you can have? If is a very simple one having 6 ammonia molecules around it. So, how will you write? So, once we decipher, once we know the names from here, which is hexaamine cobalt 3 chloride. Once we know the thing, that means when we write the name over here as hexaamine cobalt 3 chloride, we should be able to write nicely the corresponding formula of the compound. how we write cobalt, its corresponding charge, knowing the corresponding charge on it, and the number of ammonia molecules and number of Cl3, because we have several other isomeric composition where more number of Cl minus will come within the coordination sphere. So, the name will be in our hand and we will write the formula from there. In different order than its name, the chemical symbol of the metal center is written first, the ligands are written next, with anion ligands coming before the neutral ligands. If more than one anion or neutral ligands are present, will be written as alphabetical order according to the first letter in their chemical formula. So, these are the different things that we just consider, that the ligands, the naming of the ligands with anion ligands coming first before the neutral ligands. So, once the name is there, just on the element, the number of atoms is not indicated with a prefix. Since it still has to be written in the formula, it is determined by balancing the overall charge of the compound. That means, how many anions are required for charge neutralization, such as this, which is tetrafluorochromium 6 chloride, it becomes CrF4Cl2. So, we are not writing that it has 2 chloride, the italics form is the chloride. The number of chlorides we do not mention, we just only see the charge on it, the oxidation state of the chromium and how many chlorides are required for charge balance. Then it would be Cl, then it would be Cl2 or Cl3. Similarly, for amine tetraacochromium 2, we have this water, then amine functions, and we just go for the corresponding charge neutralization and we see that 2 anions would be required. So, when we have all neutral ligands, we alphabetically order them. So, with water before NH3, so water will come first alphabetically, then ammonia will come, which is opposite to that in the complex name, since one uses the chemical symbol and another uses the name of the ligands. In one case we use the names, in another case we are using the corresponding symbols. So, we have the amine sulfatochromium 2, where sulfate is an anion, so it comes before NH3. So, sulfate is in the coordination sphere. So, we go for the corresponding sulfate name first. So, amine sulfatochromium 2 when we write the formula. Similarly, amine tetraacochromium 2 sulfate is also like this. So, amine will come next, water will come first, then potassium hexacyanoferrate, we have discussed it. Then we will have another molecule which is cisplatin, and we will discuss in our next class. We will finish this part, the remaining part, that how we will name is a wonderful molecule which is cisplatin, and how we name it and how the molecular formula is coming and how the different geometries will be related to this particular important molecule. So, this particular molecule will be named like this. We have 2 ammonia molecules there, we have dichloropplatinum center is there, that means 2 amine molecules are there. So, it is basically platinum NH32 and Cl2, and now the isomeric form, some name we are writing as cis. So, this is some level that where you have, because if we have some alternative positions for the binding of ammonia to platinum center and the chloride binding to the platinum center, we name as a level which is our cis, but the basic compound is diamine dichloropplatinum. So, the NH3 groups will come, then we have the chloride functions. So, we have the molecule like this, where we have 2 of these as in the adjacent position. So, that is why it is the cis position when Cl PTCl bond is 90 degree, which are not in opposite direction, that means Cl PTCl bond is not 180 degree, it is a square planar geometry. If the geometry is in square plane, that all 4 platinum bonds two of them are platinum nitrogen and two of them are platinum Cl. So, if we see that if two of them are 90 degree, when these two positions are occupied by chloride, we call it as a cis platin, but in another case when we have Cl in the opposite direction, that means they are about 180 degree apart, we consider them as trans. So, these are two nomenclature level for the isomeric forms, one is the cis form, another is the trans form, like we use the nomenclature for ethylene molecule. The ethylene molecule what we have, that ethylene molecule can have positions like this. So, when they are opposite, so if we have the dichloroethylene, so around this double bond, so around this metal center we will consider this the cis and trans positions. So, when two of them are on the same side, we consider them as the cis. So, when in this particular case, since it is a regular square geometry, when two of them are 90 degree, that means we consider them are on the same side, we call it as their corresponding sides. That means, if they are Cl and if these are 2H, we call this as also a corresponding cis molecule, where Cl is here and the Cl is there on the opposite direction, we call it as a trans. So, this is the unique molecule. When we name this molecule, then we should also correspondingly name the corresponding geometrical form, and the full name will therefore be, when we have the corresponding compound as cisplatin, will be cis diamine dichloroplatinum. So, next day we will continue little bit and we will finish it next day. Thank you very much.